Welcome to Concept 3 Notes. We are going to be talking about periodic trends, and these are the same notes for my on-grade level students and my honor students. Now, in real life and class, I really love to do this inquiry activity with you guys first to introduce you to the periodic trends, so we're going to do that. So hopefully, if you are watching this, we have already done this activity to kind of introduce you to a couple of these trends. Now we'll dive a little deeper, okay? So what are periodic trends? They are just specific patterns in the periodic table that make it possible to make predictions about an element's properties. We've already seen that based on an element's electrons, they will behave a certain way. And what we've seen is that elements in the same group have the same number of valence electrons and thus tend to have similar properties. And so a lot of this all comes together because of the electrons we will see, but it gives us these patterns in the periodic table for atomic radius, for electronegativity, for reactivity, all of that. And so we're going to zoom in on some of these today. So a lot of these trends that we are going to see are explained by something called Coulomb's law, which is actually kind of a physics thing, but all the sciences are really interconnected. So Coulomb's law says that as the atomic number increases, the nuclear attraction for electrons also increases, thus pulling the electrons in more tightly to the nucleus. Okay, let's think about this. Let's break down what this means. Looks like a lot of words, but it makes sense based on what you already know. Okay, so first, let's break this down. As the atomic number increases, well, we know that atomic number is the same thing as the number of protons. So if the atomic number is increasing, the number of protons in that atom is also increasing. Okay? Now the next part of the law says that the nuclear attraction for electrons will increase. Well, that makes sense because if the atomic number is increasing, that means the number of protons is increasing. And if the number of protons is increasing, that means the strength of positive nuclear charge is increasing. Think about it. The more protons there are, the more positive the nucleus becomes. Thus, it's going to attract those negative electrons more, and thus it's going to pull them in more tightly. Okay, so this makes sense. The more protons, the more positive, the stronger those opposites will attract with that electromagnetic force. It's going to pull them in more tightly. And this law is going to, again, explain some of these patterns we see, like atomic radius. So let's start here. Atomic radius is the simplest way to compare the size of an atom. It's technically the most accurate as opposed to looking at just the entire size of the atom, because the cloud in an atom, the electron cloud, is not really a definitive size. So looking at the radius of an atom is a bit more helpful. So the atomic radius is just 1/2 the distance between the nuclei of two identical atoms that are bonded together. Okay, so here's what we can tend to see in the pattern. So this gray kind of represents the shape of the periodic table. What we see is as you move down a group, any of the groups, as you go down them, you see the atomic radius is increasing. Okay, so it's getting bigger. Okay, why? Well, this is because the number of electrons that are just in the atom is increasing. And so there's going to be more energy levels. Think each one of these different elements is in a different period. So there's a whole nother energy level in its cloud holding electrons. Every time you add an energy level, that's getting further and further out from the nucleus. So that makes sense that as we move down the group, the radius is going to increase. Now, the other part of this trend is looking at the period. Atomic radius tends to increase as you move left, so this direction in a period. Why? Okay, well, this is because when we're moving this direction, the number of protons is decreasing, which decreases the positive charge of the nucleus, which decreases its strength and its ability to attract electrons towards it. So it's not going to hold those electrons as tightly. Okay, so based on these patterns, the element down here would have the biggest atomic radius, and then the element up here would have the smallest. So let's think about that. So cesium would have the largest. This makes sense. Well, Technically, it should be francium, but people often say it's cesium just because we don't know as much about francium. But really, francium and cesium should have the greatest atomic radii, okay? Why? Well, they have a ton of electrons. I mean, they have 7 energy levels we're looking at here. Okay, so that makes that really big. And then also, they have they have less protons than, say, Tennessean and these other elements over here. So they're not going to be able to pull their electrons in as tightly. So the electrons in their clouds are just going to be kind of wandering off further, not held as tightly. So that makes them the biggest. Whereas when we look up here at fluorine, fluorine is going to be the smallest because first, it only has 2, fluorine and helium really. They only have, 1 or 2 energy levels, so not a lot of electrons in general. And fluorine has, 7 more protons than, it has 6 more protons than lithium in the same period as it. And so it's going to have a stronger positive attraction, positive force pulling in those electrons than, say, lithium in the same period. So this has the smallest atomic radius. Here's where we're going to see the largest. Again, backed up by Coulomb's law, which we just talked about. Okay, now let's talk about reactivity, which we did talk about a little bit in our last unit. This is just a measure of how readily an atom is going to react. And atoms tend to react in ways that will get them to have the electron configuration of the nearest noble gas. Because remember, noble gases are already stable because they tend to have the octet rule, the full 8 valence electrons in their outer energy level. So they're the most stable. So elements want to get to be like that noble gas. So like if you look at fluorine, it's just 1 away from being like neon and being stable. Or if you look at lithium, it's just 1 away from being like helium and being stable. So it wants to do that. So that's why we kind of see these funky patterns in reactivity. So first, the metals. Metals increase in reactivity as you move down and left. They become more and more reactive. This being one, think about it, all these metals that are in group 1, like lithium, sodium, potassium, if they just lose 1 electron, they're stable. So they really, really, really want to lose that electron, especially something like cesium, which isn't even we already saw it has such a big atomic radius. It's not even holding that 1 electron very tightly. Like it's so easy for it to let go of that electron that it makes it really, really reactive. Whereas on the other side of the periodic table, we have our nonmetals. They increase in reactivity as you move up the group and right. Because again, think about the atomic radius. Like fluorine is holding its electrons tightly. Like it's holding those 9 tightly. It just really, 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 really wants 1 more. It only needs 1 more to be just like neon. Okay. And then you'll kind of notice here, like some of these are kind of blacked out. We see some interesting patterns when we get in the middle here, especially like these elements in group 14. Like it's not any easier to gain for or lose for, and so we often see that they're going to share, so they're just not going to be as reactive as these ones on either end of the periodic table. Now again, this is like just a glimpse into what we're going to see in our next unit, which is all about bonds and why elements will react to form bonds and become more stable, but I just want to kind of introduce that to you here. Okay. Another kind of, I don't know if you'd even classify this as a trend, but it's just an effect. It's something that happens because of these periodic trends that we see, is the shielding effect. So we talked about electrons in the outermost energy level of the electron cloud are valence electrons, and then all the others are core electrons. So the shielding effect is when electrons in the inner energy levels, like those core electrons, they block the attraction of the nucleus to the valence electrons. So if you have so many like electrons as your core electrons and so many energy levels between the nucleus and then the valence electrons in the outermost energy level, they can just start to block that positive charge and that positive attraction from the nucleus, and then that makes the valence electrons held even more loosely, and they are even more readily available to be, given away to form bonds in order to be stable, like we see in cesium. So similarly, this increases as you go down a group and the atomic size is increasing, which we see. And again, it's because as atomic size is increasing, the more total electrons there are in the atom, the bigger it's going to be. The bigger it is, the more energy there are to block the positive attractive force of the nucleus. The more that attractive force gets blocked, the greater the shielding effect on those valency, and the more likely they are just to leave and react, and so that the element can be stable. All right, now this is another periodic trend that's super important we understand, because really so much of chemistry comes down to electronegativity. Okay, so what is it? It is a measure of the ability of an atom in a bond to attract electrons. Okay, so the bigger the electronegativity, the more strongly the atom is attracting E. Okay, so think about it. Which elements do you think would have the greatest electronegativity? Which ones are going to attract E the most? Versus which would have the smallest E and attract E the least? And then what do you feel like the noble gases electronegativity would be? How much are they attracting electrons? A lot or a little or not at all? Okay, think about these things. We're going to discuss them in class. Okay, so what the trend is for electronegativity is it tends to increase as you move up a group, and then it tends to increase as you move right in a period. So we tend to see that the things in this direction, like moving towards fluorine in the periodic table, tend to have the greatest electronegativity and ability to attract E. And then the things over here, and kind of the cesium direction, tend to have the least ability to attract electrons. Now, one cool thing we can do, and this is going to come up a lot in our next unit where we talk all about bonds, is we can calculate the difference in an electronegativity between two atoms. So the delta En, the change in electronegativity between two atoms. And the greater the difference, the stronger the E are going to be pulled in one direction. So like the less shared they are. And then if there's not a very big difference at all, then they'll be very equally shared. Okay, so for example, if you calculate the difference in electronegativity between two atoms and it ends up being greater than 2, those two atoms would form an ionic bond, which is where one atom, which is typically a metal, and then another atom, which is a nonmetal, they're going to give E and one's going to take E. Okay, so the metal, which is on the left side of the periodic table, is going to give up its electrons. The nonmetal on the right side of the periodic table is going to take those electrons and they're going to form a bond. Okay? Now, if your difference in electronegativity is less than 0.5, that's going to be a covalent bond where there's not a very big difference between their electronegativity, so no one is really pulling the electron more strongly than the other. And so they're going to share the electrons. And we tend to see this between two nonmetals that are going to share E. Now, what if your difference in electronegativity falls between these two extremes? If it's between 0.5 and 2, we call this a polar covalent bond. So what that means is that the electrons are going to be shared because it's covalent, but they're going to be unequally shared. Polar just means that one side will be a little bit more negative because that atom pulls the E that are shared just a little bit more, and then the other is a little bit more positive. So it kind of has poles within the sharing. I think about my two preschool age children. They share toys all the time, but my oldest is a little bit more strong-willed than my youngest one, and he tends to boss her a little bit more. So yeah, they may be sharing, but he's kind of pulling the reins a little bit harder than she is when they're playing with the toy. And so it's a covalent bond, but it's definitely polar. Okay, so we're going to practice this where we'll look at those numbers and we'll do the subtraction, and you'll be able to predict the type of bonds that two atoms will form with each other based on these numbers, which is pretty cool. So that's what we're going to stop and do now in class. But for the sake of the video, we just have a few more slides that we're going to hit. Okay, a couple more periodic trends I want to touch on. One is ionization energy. Okay, so IE, this is the energy that's required to remove one electron from a neutral atom of an element. So how hard is it? How much energy is it going to take to make something a cation if I'm going to take an electron from it, or an anion? So this increases as you move up a group and increases as you move right in a period, which makes sense. Think about fluorine. Again, it has 7 valence electrons. It only needs one more to be stable. It's going to take a ton of energy to remove an electron from fluorine and make it an ion, okay? Because it does not want to have electrons removed from it. It wants to take electrons from other things. It just wants to take one more. So that makes sense. Now, another thing that's interesting is that ionization energy that is removed. So as you remove one electron, it might be easier to remove the second one. It might be harder to remove the second one. It just kind of depends. So remember, removing an electron gives an atom a charge, and charged atoms are called ions. We've talked about this. I think we've talked about this now in like 4 sets of notes, but like I really want you to know these terms, and they're going to come up again in our chemical bonds unit next. So cation has a positive charge because it has lost electrons. Anions have a negative charge because they have gained electrons. Okay, now, you know what? I'm actually not going to say what I was just going to say. We're going to leave it at that and not make it more complicated. Now, something I do want to introduce you to, though, are oxidation numbers. And you've seen these before because I showed you these in previous notes that we did. I believe it was Concept 1 notes when we looked at magnesium and we looked at oxygen and how magnesium becomes a cation and oxygen becomes an anion. And we wrote Mg plus 2 and we wrote oxygen minus 2 in our notes. Those numbers that we wrote are called oxidation numbers. Those are the charges of an ion, okay? And we write them as a superscript to the right of the symbol. And so what we see is that ions that will most likely form are based on where they are on the periodic table because it's a periodic trend. So for example, elements in group 1, we're talking lithium, sodium, potassium, rubidium, they all have one valence electron. So when they form ions, they tend to lose that one valence electron to be stable, which gives them a +1 charge. Elements in group 2, beryllium, magnesium, calcium, those elements have 2 valence electrons. So typically when they form ions, they will lose those 2 in order to become stable, and that gives them a +2 charge. We always are going to skip those transition metals because, again, their electron configurations get complicated. They can kind of do some different things, so we're not going to worry about those for this. Group 13, they have 3 valence electrons, so they tend to lose those 3 and get a +3 charge. Now, group 14 is where it gets interesting. They have 4 valence electrons, so it's just as easy to gain 4 as it is to lose 4. So they can have a +4 charge or they can have a -4 charge. It just kind of depends. We tend to not even really see these have a charge because they tend to share their electrons, which again, we'll get to in our next unit. Group 15 elements have 5 valence electrons. It is easier for them to gain 3 electrons than lose 5. So they tend to have a -3 charge because they're gaining 3 electrons. Group 16 have 6 valence electrons, so they have a -2 charge because they're going to gain 2 electrons. And then group 17 have 7 valence electrons, so they just are wanting to gain 1. Fluorine, chlorine, bromine, those halogens, all they want is 1 electron to be stable. So they'll get a -1 charge in order to do that. And you can write these across the top of those groups on your periodic table if you want for reference so you don't forget those. Okay, the last trend we're going to talk about is ionic radius, which is how we're going to compare the size of ions. So again, when atoms become ions, their radii are going to change because they're either gaining or losing electrons. And so that changes things. The way we measure an ionic radius is by measuring the radius of a monoatomic ion within an ionic compound. So looking at sodium within a sodium chloride compound. And what we see is that atoms that lose electrons, so these would be cations, which tend to be metals, they are going to become smaller. And atoms that gain electrons, or anions, are going to become larger. And we see an increase as you move down a group. Okay, so why do you think that is? Well, let's think about anions. Anions are going to become larger because the nucleus of an anion, like of a fluorine atom, is not getting any more positive. So it isn't, as it's gaining electrons, it's not going to be holding them as tightly as before. Whereas, think about, so they're going to be more spread out, larger. Whereas with cations, the attraction of the positive nucleus is going to become stronger because as they lose electrons, that more positive is going to pull in the remaining electrons and hold them more tightly. And so that's why we see them become a little bit smaller. And then again, we see this increase as we move down a group, because as we're moving down a group, they have more protons. And so that's what we're seeing there. Now, we don't have a trend in period because, again, as you move across a period, you go from cations to like things that are more going to share electrons to anions. So there's not really a period trend as much as there's a group trend, and then these two distinctions here. Okay, so we're going to practice this by playing a little game together where we figure out which element is going to go which way in a periodic trend based on what we just learned about.